Hello and welcome to a video on the definition of logs and how we're going to use logs to find x-intercepts of exponential functions. Okay, so we have a lot to cover in this video, and we're going to start out by just reviewing what an exponential function is. So an exponential function, there's really two types. There's growth, so f of x may be something like 2 to the x, which looks something like this, a function that's growing quickly like that. And then approaches the x-axis towards the left. And then the other example would be f of x equals 1/2 to the x, and that's an example of exponential decay that looks something like this, and that is a function that starts out big, but it gradually gets smaller and then gets closer and closer to 0. Okay, now both of these functions have a lot in common. First of all, the domain and range are the same for both of these. The domain for these is all real numbers. And the range for both of these is everything greater than 0. And something else is really important about these two functions, and that is that either they're strictly increasing, like the growth function, or they're strictly decreasing. And what I mean by that is a function that's strictly increasing will go up and up and up, and it will never turn back and go down. Now what happens as soon as it turns and starts to change its direction from an increasing to a decreasing is at that moment it will fail the horizontal line test. So an important thing to note about all exponential functions, no matter what kind of transformation or whether it's growth or decay, is they will always pass the horizontal line test. You're never going to find a horizontal line that crosses more than one point on an exponential function. Lost the function there. Okay, so the horizontal line test indicates that these are one-to-one functions, and when they're one-to-one functions, that means that they have an inverse. Okay, so that means that if we were to look at a function and look at the points on the function, we have, for example, 0, 1. This has the point 1, 1/2. And of course it has infinitely many points. And if we took all of those points and we switched their x's and y's, we would have points like 1, 0, 1/2, 1, and a whole list of points, but we would never have a repeated first coordinate, because that would indicate that it's not a function. So these are all invertible, which means they all have an inverse. Now what we're going to do is we're going to go ahead and look at a new definition, which is going to be how we're going to find the inverse. Now our goal is to take something like this, y equals 2 to the x, and it could be any base. We want to take something like this and we want to be able to solve for x. So that's actually our goal, is to be able to write x, which is in our exponential function, x is an input, and we want x to be an output, and we want y to become the input. And so we'll see why in a minute, but the way that we do this is something called logs. So notice that the base here is 2. Well, I'm still going to write a base of 2. And I'm just switching the x's and y's. So this works in both directions, but in equivalence, these are equivalent statements. So another way to say y equals 2 to the x is to say x equals log base 2 of y. Alright, so we're going to go ahead and just, for example 1, we're just going to practice taking the exponent out and moving it from that position of being an exponent to being the output. And we're going to take the output, everything in this y position, and we're going to move that into the position of being the input with the logs. Okay, so we take whatever's up there in the exponent, right up there, and we just say that, which in this case is 3, equals log, and we keep the same base. 1.2 is the base before, 1.2 is the base now, and it goes a little bit lower to indicate that it's the base, and we say 3 is log to the base 1.2 of m. Okay? Here we're going to take the b, and b is log to the base e, the same base of 9. Just switch the input and output. Here we're going to take the 4 and say 4 is log to the base a of 24. Okay, that's how you write them. Now, what would be really helpful here is we could actually evaluate some of these that have numbers. Like, for example, the second one, part b here. These are both numbers. Log to the base e of 9 is just a number. The other two have variables in them, so we wouldn't be able to evaluate those. But here's something called the change of base formula that's going to help us to use our calculator. So this is going to be just a rule that's universal that says log to the base a of b is the same thing as the log of b, the one that's higher up, over the log of a. Now if you look on any scientific calculator, they have a log button. And this video is not about what exactly that log button means, but it's a function that the calculator can, it's something the calculator can calculate, and if you have a number, you can apply it. So that's what we're going to do down here, for example, 2a. We're going to just, in this case, a is 2 and b is 3. So we're going to say that log to the base 2 of 3 is equal to the log of 3 over the log of 2. And then when we look in our calculator and we actually just find that log button and just hit log 3, make sure if there's a parenthesis around it that you close that parenthesis before you divide, and then divide by log 2, and that will probably give you a parenthesis, and then you have to close that parenthesis. Alright, this is approximately equal to 1.58. So this is approximately equal to 1.58, because the change of base formula says that these two things are the same thing. Alright, well now we can use our log definition, what we have up here. We can use the arrow in the other way and we can see what this actually means in terms of exponentials. So what this means, what this means is that 2, so this meaning that 2 to the 1.58 is approximately equal to 3. I just switched this from log form to exponential form using the same process as up here, only backwards. And if you punch that into your calculator, you're going to find that it's very close to true. It's, of course, where there's rounding error, but that's it. Alright, let's look at another example of using the change of base formula to evaluate. And here's another log, the opposite of the log to the base 3 of 2. So this would be the same thing as the opposite of log 2 over log 3. So you can find log 2 over log 3 the same way that we found log 3 over log 2, and then you just take the opposite. And when you do that, you're going to get approximately negative 0.63, which means that this is approximately negative 0.63. Whoops. So if you cancel the negatives, what this is also saying is that this means that 3, the same base, 3 to the 0.63 is approximately equal to 2. Okay, so this gives us a way to figure out what we raise a number to a power, what power we raise a number by in order to get an output that is a desired output. Okay, we can continue this process now to find x-intercepts of functions. So if we're looking at a graph, something like this first one, which we know that this is approximately a graph that looks like a growth function that's moved down 3 units. So there's an asymptote down here somewhere, right? And we know that one above there is a point. And we know that if you go over 1, then there's another point 2 above there. So it's something like this. This is a very rough graph. But the important thing here is that it crosses the x-axis. This has an x-intercept. And so what we want to know is, what is that x-intercept? And x-intercepts are always the x value where the output is 0. So we can find this x-intercept in the normal way by setting 0 for y, or for f of x. So 0 equals 2 to the x minus 3. And now we have a way of solving this for x without logs that we didn't have that. So we're going to add 3 to both sides, and we get 2 to the x equals 3. And then we're going to go ahead and use our log definition to say this means that x equals log base 2 of 3. And we just found that. We just found that up here. Log base 2 of 3 is about 1.58. So that tells us this x-intercept is about 1.58. And by the way, it also tells us that 2 to the 1.58 is approximately equal to 3 from this equation right here. Okay, let's try another one. So let's look at a more complicated equation, and see if we can find the x-intercept of this one. Alright, so let's go ahead and do the same thing that we always do, which is to set f of x equal to 0. So we're going to start out with 0 equals negative 2 times 5 to the negative x plus 4. Let's go ahead and solve this. So we're going to subtract 4 from both sides. So we get negative 4 equals negative 2 times 5 to the negative x. And just to be clear, we're going to divide both sides by negative 2. So I'm showing this step. And so we get positive 2 on the left side equals 5 to the negative x. At this point, we're ready to now use the definition of logs and say, well, I want to solve for that exponent. Actually, I want to solve for the opposite of it, but I'm going to start out by just solving for the exponents. The exponent comes out in front. So we get negative x is equal to log to the base 5, same base, of 2. Which means that x is equal to negative log of 2 over log of 5. And you can put it in parentheses, it really doesn't matter. You can just divide a negative by a positive. And when you do that, you get approximately 0.43. So this tells us that if we were to graph this function, which we're not going to do, but if we were to graph this function f of x, we would have an x-intercept at 0.43. It also tells us that if we look, like let's say right here, so the meaning of this as far as exponentials would be that 5 to the negative 0.43, oh sorry, this is negative 0.43 right here, this is a negative, and so 5 to the opposite of a negative 0.43, which is 5 to the 0.43, is approximately equal to 2. Okay? Alright, let's look at the other rule about logs that that's going to make using our calculator kind of handy. Now we could do these without the rule that I'm going to show you, but I'm going to show you a rule. Now the log, remember that e is the natural base. So we can say that log to the base e is the natural log. Alright, so that's what we're going to do. We're going to say that log to the base e of anything, okay, is the natural log of that thing, whatever that is, a, 2, whatever it might be, okay. ln stands for log natural. It's from Latin roots, so it comes in backwards. So but it's natural log. Okay. So let's apply that real quick to a couple of these examples here to evaluate. This is easier. We don't need the change of base formula because we have ln. Now, if you look on your calculator, there's an ln key, and all you have to do for these is just hit ln of 3. And when you do that, you're going to get approximately 1.098. That means that e to the 1.098 is approximately 3. Okay, this is just the check. This is what it means. All right, you don't really have to do that last step. All right, let's try one more like that. So why don't we try this? See if we get the same answer. And this is approximately negative 8.96, which means ln of 6. Well, this is the answer, by the way. Now the check, so this the means. ln of 6 is approximately negative 8.96 over negative 5. Negatives cancel, and you can say e to the 8.96 over 5 is approximately 6. Okay, try part C. Pause the video and see what you get. Okay, so if you got this far and then you try, this is not ln minus 3, it's ln of negative 3, and you try this, you're going to get an error. And why is that? Because e to the x plus 3 is just a growth function that's moved up, something like this. It has no x-intercept. So this error means has no x-intercept. Okay, try D. Okay, so there's the process. You end up with x equals 2 ln of 2, which is approximately 1.39. That's the x-intercept of this function for part D. And this means that e to the 1.39 over 2 approximately is equal to 2. Okay, I hope you found this video helpful.